Hello, let me try to explain the next phase of the code. Now, in the current code, what we do is we take points along a circle of radius r, and using the IFFT, we find the values of the polynomial at these points. Then we search for local minima of the absolute value of the polynomial. So let us suppose that Zj is a local minimum of these values. You have already written a code to find these local minima. Right. So let me write Zj as r e to the ij. Right. Now what I'm going to want to do is take the neighboring points and take the polynomial values at these neighboring points and use that to find the coefficients of a cubic polynomial. So I'm going to interpolate a cubic polynomial through the values of the polynomial at these 4 points. Notice Zj is the point where the minimum occurs. I take 1 point to the right and 2 points to the left. Right? So if I want to get my values of z, I have 4 values of z. I'm going to arrange these in a single vector. So this is Zj minus 1 here. This is Zj. This is Zj plus 1. This is Zj plus 2. So notice all of these are multiplied by Zj. You see, to get Zj minus 1, I take Zj and multiply by e to the minus I delta, because I'm rotating clockwise by delta. Similarly, to get Zj plus 1, I multiply Zj by e to the ij, because I'm rotating clockwise by delta. Here I'm rotating clockwise by 2 delta. So that gives me this vector zvec. I also have a vector of polynomial values at these 4 points. So let me just specify that. These are the, whoops, let's do this. These are the polynomial values at the 4 points. All right, so what we want to do is, as I said, we want to interpolate. We want to find coefficients. Now, I'm sorry, these a's have nothing to do with the original avec. These are new coefficients. So you want to interpolate a cubic polynomial. All right, so that means I need to find a0 up to a3 such that these equations hold. My interpolated polynomial looks like a cubic like this. All right, so P0 is the value at this point. Actually, it's at Zj minus 1. P1 is the value of the polynomial at Zj. P2 is the value of the polynomial at Zj plus 1, and so on. But all of these I'm expressing using the same cubic. And the cubic coefficients are a0, a1, a2, and a3. So notice that this is a0 plus a1 times Zj minus 1 plus a2 times Zj minus 1 squared plus a3 times Zj minus 1 cubed. Right? This value here, e to the I theta r, that's Zj, times e to the minus I delta, this product is Zj minus 1, just like I mentioned up here. That's the same as this product here. So here I have a1 times Zj minus 1, a2, Zj minus 1 squared, a3, Zj minus 1 cubed. P1 is the value of the polynomial at Zj. Right, you see Zj is here. It's 1 times r e to the ij. The value of the polynomial is P1. So P1 is equal to a0 plus a1 times Zj plus a2 times Zj squared plus a3 times Zj cubed, and so on. I have Zj plus 1 and I have Zj plus 2. All right, so here I have 4 equations in my 4 unknowns, a0, a1, a2, a3. And again, these a's have nothing to do with the original a's that define the polynomial. All right. Now I can express this sequence of 4 equations here, I can express as a single matrix equation. I can express P as a vector of 4 entries. The coefficients I can express this way. And then I write A prime. So let me define A prime here. A prime is a little bit different from A, but this makes the solution more easier. A prime is going to be, notice that here I have consistently A0, A1 e to the I theta r, A2 e to 2I theta r squared, and A3 e to the 3I theta r cubed. And that's consistent throughout the 4 equations. So my A prime is going to look like this. A0, my first entry is A0. Let's see, where am I? Okay, my first entry is A0. That corresponds to this entry here. Then I have this entry is the second one, which is A1 e to the I theta r. And next one is A2 e to the 2I theta r squared. Last one is A3 e to the 3I theta r cubed. All right? Now, if I solve for A prime, I can easily find A0, A1, A2, A3 because I know theta. I'm sorry, this is not theta. This this is theta. This is theta. Yes. Okay. All right. Because I know if I find A prime, I can find A0, A1, A2, A3 because I know theta and I know R. So it's easy enough for me to find A given that I know A prime. So in this section of the code, I just want to focus on finding A prime. All right. So here's my matrix equation. P equals M times A prime. So A prime, if I solve for A prime, I simply get A prime as M inverse times P. Now notice M inverse is M is a fixed matrix. So M inverse is also going to be a fixed matrix. So I only need to compute M inverse once. Okay. All right, now I mentioned this for one particular value of Zj. But in the code that you just wrote, you found several values of Z where there was a local minimum. So we want to do this interpolation for every local minimum. So here's a code outline, and you can implement this code. Okay, so we'll let n be the smallest value of 2 that's greater than or equal to the length of AVEC. Now this is already in the code, but I just want to define this n. So this is already in the code. So we have delta is equal to 2 pi over n. So delta is actually the rotation angle between successive points. Now construct m and m inverse as above. Remember that m depends only on delta. So once you have delta, you can find m. Once you have m, you can find m inverse. If you don't know how to invert a matrix in Python, you can look that up on the web. Okay. Now, for each entry 1 in INVEC, this is the INVEC that you just found. For each one entry, first you select the 4 neighboring values of PVEC. And note PVEC is complex in this case. You want to arrange these values into a 4 by J matrix. So I'll explain what this means in a moment. I'll give you an example. J is the number of entries is the number of 1 entries in INVEC. Right? For every 1 entry in INVEC, you're going to get 4 values of P. All right? And you're going to arrange these into a 4 by J matrix. Then I multiply M inverse by this 4 by J matrix. Right? So each column of the result will be the coefficients. Well, this is going to be the A prime of a different cubic. Okay. So for instance, if I have 5 different minima, I'm going to have 5 different cubics. And then we can find the roots of those cubics separately. In fact, we can do that in parallel. We already have code that does that. I will let you know in advance that I found a solution of a quartic. I may want to switch to a quartic. But since the procedure is similar, the changes will not be much. All right, so let me give you an example to show what the kind of result that I want. Let's suppose that n equals 16. All right, so when you write your code, you can write your code in a separate code file, create a new file, and write your code, and you can test it with this, with an example like this. So you can set n equal to 16. Delta will be equal to 2 pi over 16. Using that value, you can create m inverse as above, all right, as I indicated. And of course, these notes are also in OneNote. You can see the label of the notes is cubic coefficient code. It should be the last page in the OneNote notebook. All right. All right. So for each one entry of INVEC, so here we are for each one entry of INVEC, I want to select the 4 neighboring values of PVEC. Here, note PVEC is complex. Oh, no, I'm sorry. I'm in the wrong place. All right. All right. So here's an example. So here, suppose my INVEC looks like this. Now you can hard code this in your test, okay? Just so that you have a test. So in this case, j equals 5 because I have 5 values of 1. All right. Now PVEC is also going to have 16 values. If you check, you'll see this has 16 values. PVEC will also have 16 values. You can put some arbitrary values in here, arbitrary complex values to test your code. All right. So from this, we would create a 4 by j matrix. Now, what would the 4 by j matrix mean? Be. Notice that the 1 here is in the 0 place. Okay. Let's see. I think I actually didn't do this correct. Let me do it again so you can see how this is coming together. So it's good that I didn't do it correctly. So, oops, sorry. Let's try again. But this is good. We can do this together. All right. So what is my Pmax going to be? First of all, my first minimum is at index 0. Okay. Now notice that I'm taking I'm taking 1 point to the left and 2 points to the right. So I want to put a P0 here. And here's going to be P minus 1, but P minus 1 is the same as P15. Okay. But you know you can refer to this as PVEC of minus 1. That's fine. And then this would be P1, and this would be P2. So these are the 4 neighboring values around the value of P0. All right. Now my second one, this is 0, 1, 2, 3, 4. My next one is P4. So I'm going to take 1 to the left, which is P3, then take P4, then P5, and P6. All right. Next, so this was P4, 5, 6. So this is going to be P6, 1 to the left, P5, P7, P8. Okay. Then this one, let's see, that's 6, 7, 8, 9, 10, P10. So P10 is here. I'll have P9, P11, P12. So I'm just doing this to show you can test your code and make sure that it's consistent with this example. So this one was P10, 11, 12, 13. So this is P13, P13, P12, P14, P15. All right, so that is your matrix. That's going to be your matrix. And then the cubic matrix, which has the matrix of cubic coefficients, is your M inverse, which you've already computed, times P matrix, which is the matrix up here. And as I said, the columns of this result will be coefficients of cubic polynomials. And for each of these cubic polynomials, we will find cubic roots. Okay, so that's the next step in the code. I hope you can see where this is going and see what you can do with this code, and then we can debug it when we get together again.